Today we will study alternating current. We have already seen current earlier, a lot of topics in current, but they were all direct currents. What do you mean by direct current? Direct current means if you have a battery and if you have any circuit, the voltage that is supplied, if you plot time versus voltage, it is more or less constant. As opposed to this, you have another type of current which is called alternating current. Which if you plot against time, it is not constant, rather it is sinusoidal in nature. This could be 0, or if you want to drive it through origin, it looks something like this. This is voltage, this is time. So you see here, the voltage is not constant. It is sinusoidal. Like a sine wave. This is the positive cycle, and then followed by negative cycle, again positive cycle, and so on and so forth. So the value is not constant, but it has certain characteristics like any sinusoidal wave, which is that this current can be represented as where this is instantaneous value, this is the peak value or the amplitude, this is the angular frequency, exactly like waves we have studied earlier. Okay. Now, as we see that this voltage goes through positive cycle, negative cycle, positive cycle, negative cycle, it makes certain calculations very tedious for us to perform and to understand. For example, if you want to calculate current, heating capacity or work done, then if you see the power in a bulb, then earlier we could, in a DC current, we could simply multiply current by voltage and it will give you power. But in this case, we cannot do it because I is changing, voltage is changing from negative to positive. So does it mean that the power consumed will be 0? No, it won't be. But if we analyze the whole process, it becomes slightly tedious. So as to make this process simple, what we do is we define certain terms called RMS. Root mean. What we do is, for example, for an instantaneous value of current, instead of taking this value, we take the average of this value, square of the average of this value, for example, over a time period, integrated and divided by 1 by time. This will give us average square value. And then what you do is, suppose this was whatever I dash square. So what we do is we find the average square of the instantaneous value over a time and average it. And then what we do is we take square root of this value. This becomes RMS value. Now, what is the advantage of this RMS value? The biggest advantage of this RMS value is that it gets rid of the cycling, negative, positive, negative cycling, because we have taken the square. So this cycle is treated exactly like this cycle, and for most practical purpose it is. So what we do is we define both the current and IRMS as well as voltage RMS. And this value numerically is, if we take instantaneous voltage, this also divided by square root of 2 of value. We take, this is the instantaneous, this is the amplitude or the peak value. So what we do is we take peak value of current and voltage divided by root 2. It gives us the respective RMS values. Okay. Now let us study an LRC circuit. First, we take the case of a capacitor. This is a capacitor, and this is our power source, which is a value varying with time. Okay. Now we know for a capacitor, Q is equal to CV is equal to and we know that dq by dt is equal to C this, when we differentiate, we get multiplied by Cm omega. So if we write it properly, it is this cos we get by differentiating sine part of it. So this was our dq by dt is equal to and dq by dt is nothing but I. So instantaneous value of I is defined like this, and if we define the peak value of this, the peak value will be when cos omega t is maximum. So we can say I naught is equal to or we can also write it like this. Why we write it like this? There is a reason for writing like this. The reason is that we want to convert everything look like? You remember in DC current, we always wrote I is equal to V by R. So we want to bring AC treatment in line with DC treatment. So this becomes our sort of a resistance. In case of a capacitance, this is called, this term is called reactance, right? And we can also write this term, we going to rewrite in terms of cost function. The cost function will be so you see our voltage source was sine omega t, but the current that we get out of it is omega t plus pi by 2. Which means that current is leading voltage by pi by 2. Similarly, we take the case of an inductor, pure inductor. This is a symbol of AC voltage. Inductor has an inductance called L. Then we know that the voltage this voltage is equal to minus dL by dt, right? And from here we can find out I, which is and we can write it like this. This is just writing cos function converting back to sine function, as we did in case of capacitor. We converted the current cos function of I into sine function. And when we did it here like this, then what we notice is this is minus pi by 2. So in case of inductance, the current lags voltage by 90 degrees. Now, if we combine all three components, which is R and C, let's see the combined treatment. Before we do that, what we define is, we define their equivalent resistances for each component, so that we can write I is equal to epsilon naught by Z. Z is some sort of a equivalent resistance, so that It looks very familiar, like a DC circuit. Z for resistive circuit is only resistance, nothing else. Z for capacitive circuit is, we've seen earlier, this. For a capacitive circuit, it was coming like this. And for an inductive circuit, it is, now if we can also write I max, peak value would be, so this become our reactance for an inductor. So Z for an inductor is how much? This much. Now we are ready to find the current in a AC circuit. So the effective Z is equal to R square plus, where so our Z becomes R square plus 1 by 1 plus C minus right, and our current becomes right. This is equal to so much. And when we do this thing, there is a phase angle added to it. This phase angle is on account of phase difference between current and voltage. And how much is this phase angle is defined by the tan of it. Tan phi is defined as which is equal to so to find phi, what you have to do is you first find tan of it, and then you take get the inverse of it to get the phase difference between current and voltage. So here, if we see, if we can write the current lags or leads depending upon value of phi. We don't know whether it will be lagging or leading, whatever. It depends upon value of phi. And the tan theta of that phi is given by this formula. Okay. Now, next topic is resonant frequency. We have seen this formula that this formula I'm going to repeat it. The peak value is when is this expression maximum? This expression is maximum when this is 0. R is whatever R is, but if this becomes equal to this, then this expression becomes 0 and the total expression becomes maximum. So I is maximum when this term is equal to or now for us, this particular frequency is of very great interest, and we call this as resonant frequency, and we denote it at, this is called resonant frequency, which makes I go to maximum value. Now, if we plot this function, which is a peak current vis-a-vis omega, the functions look something like this. On this axis, we take omega. And on this axis, we take phi. And we will see this curve is something like this. Current is maximum at resonant frequency, right? And the sharpness of the peak is dependent upon a term called quality factor, which is equal to now if we take at I naught is equal to I max by root 2, then it corresponds to two frequencies, this one and this one. And the difference between the two is twice the difference in frequencies. I repeat, let's take a point on vertical scale, vertical axis, I naught, which is I max. This is I max by root 2. This value at this, for this I, we will get two frequencies, this one and this one. And the difference between the two frequencies is 2 delta omega, right? So this is also equal to omega naught by 2 delta omega. Here this is the resonant frequency. To get maximum better quality, this factor should be maximized, which means this factor should be minimized. It basically means that sharper this peak, narrower will be 2 delta omega. So our aim is to get, for good quality, peak should be narrower, which means should be low, because it is in the denominator. This is a factor, this quality is very much important when you're tuning your radio. When you tune your radio, you would wish that for a very narrow band, you should get your peak value, and peak value means you have tuned to the proper station. Next, we study the power in AC circuit. What we do is, to start with, let our I be equal to, in a power circuit, in an AC circuit, let our I be represented as and our voltage okay. This is the phase difference between current and voltage. Okay. Then what is our power? Instant power is equal to, this will be sin omega t into if we separate out, this becomes into this becomes cos 5 minus cos of 2 omega plus Now, we've seen that in a cycle, the average value of this factor becomes average over a cycle is 0. So our power becomes you can say that this is equal to this we can write as IRMS into VRMS cos phi. This cos phi is the phase difference between current and voltage. This particular cos phi has a special name. It is also called power factor. Why is it called power factor? Because this is a factor to which you have to multiply with I and V so as to get power. Power is not simply I and V, it is also multiplied by another factor called power factor. Next topic is LC oscillations. Here what we do is we take an inductor, this is our inductor, this is our capacitor, this is our key which can close or open the circuit. Now to start with, C is fully charged. And L has no charge. Okay, this is our starting condition. Then we know for a capacitor, Q by C is equal to Q by C is the voltage across the capacitor, which will be available to inductor. And this becomes dt, which means voltage is equal to Q by C C minus N 0 from here only. This also implies that Q by C, I is again dq by dt. So this becomes double differential of Q by dt square. Since Q is discharging, the sign becomes positive. So what we get is Q by C plus N d square Q by dt square is 0. Now, or we can also say that Q by NC plus Now, if we compare an equation of a simple harmonic motion, wherein we know that for a body which is undergoing an acceleration because of a force, this is displacement. Just to explain once, recall, this is a typical case of a spring and mass. The force is X is the displacement from the stretched position. If the spring is stretched by X, it produces a force which produces acceleration. So this is a typical force equation in mechanical SHM. Now, if we compare this vis-a-vis this, is a similarity, and the similarity is, sorry, before we do that, what we'll do is, this is m d square x this expression, we can write it in terms of x displacement. And now, if we compare this equation with this equation, what we get is, here we are talking about x, here we are talking about q. So if we take an equivalence between these two equations, you see that m is equal to 1, d square x coefficient was m, here it is 1. And what is the coefficient of x here? It is k. So k is equal to coefficient of q. Coefficient of q is 1 by LC. So what these two equations tell us is that this function will behave like this, and this function we have already seen umpteen number of times behaves like simple harmonic motion. So this circuit will also behave like a simple harmonic motion. What does it mean? Let's see. So we resolve this. For this equation, we know time period is equal to is given as m by k or omega is given as k by m. This is so because we know t is equal to 2 pi by omega. So this gives us omega is equal to so much value. And in our case, K was L by C, 1 by L by C. So omega is M was 1. So what it means is that this this circuit will behave like a simple harmonic motion with angular velocity, angular frequency as omega naught. So we can write the expression as Q is equal to Q naught, which actually is Q max, to cos frequency will be the same as this frequency, plus some phase angle. I is equal to dq by dt is equal to omega Q max sin omega t, which implies that I max will be so the maximum current in this circuit would be given by this phenomenon. Now what happens is at time is equal to 0, capacitor is fully charged. And as the time passes by, capacitor starts getting discharged. And it goes on till Q becomes 0. At that time, I is maximum. Now what happens? When charge becomes 0 on a capacitor, when a capacitor charge becomes 0, all of its energy is gone into inductor. Now what happens is inductor will start charging capacitor to full capacity until this charge on L becomes 0. So this cycle keeps on, L charging C, C charging L, keeps on going at a frequency omega naught. And the energy stored in a capacitor is and the energy stored in inductor is so what will happen? This energy will get converted to this energy will get converted to this energy, and this cycle goes on. And write it as 0 plus the frequency is again 1 by H. So next topic is transformer. I'm sure everybody has heard this term called transformer. What is the purpose of a transformer? The purpose of a transformer is to change level of input voltage. If it can increase, or the output could be, say, output increased or output decreased. If output is increased, we call it as a step up transformer. If the output is decreased, we call it step down transformer. Okay. So how does it look like? Basically, transformer is a ferromagnetic core on which one side is called primary side and similarly you have coil wound on the opposite side. This side is called secondary side. Primary side is called because this is where we connect the power supply. And this is normally called this is the input side and this is the output side. Now, because of the geometry of the transformer, voltage across primary is equal to number of coils in the primary, rate of change of flux. Similarly, voltage across secondary will be number of coils in the secondary. Now, it is interesting to know that this d phi by dt in both the cases is same because it is the same flux which is linked in both the coils. So if it changes anywhere, it changes everywhere. So this gives us a special equation. It means that the ratios of the voltages across primary versus secondary is same as number of turns in primary versus secondary. This E can be replaced by voltage also. And we also have, since all the power here is transferred to all the power here, assuming there is no losses, then what you have is IP and ISM current in primary. This is current in secondary power.